The next speaker is Xianyi Yuan, who is from Hong Kong University of Science and Technology in Guangzhou, under the supervision of Professor Guoming and Professor Deke. He will present his work on fine-grained energy accounting for production LLM survey, which provides request-granted energy information to support for accounting and future energy providers.
Okay. Hey, good afternoon, everyone. I'm Yuan. And today I would like to begin with a surprisingly simple question. And when many users share one service, who is responsible for the energy? This is also a networking question. A production LLM is not an isolated model running on a single GPU, and it is a network service. A request enter through an API gateway, and a router sends them to a different server, and a scheduler decided which requests run together. And this question determines not only latency and throughput, but also energy consumption. And today, I'll first introduce how production LLM serving works, and then explain the energy attribution problem, and present our key idea, and finally show our system and results. And first, I'm going to introduce the preliminary of LLM serving. And inference has two stages. And during the first stages, the preview stages, the model reads the prompt and building the initial KV cache. And this phase is highly parallel and compute intensive. And during the second phase, the decode phase, the model generates tokens sequentially. And even every new token looks back at the growing KV cache. And this phase is often limited by the memory access. And the production answering, there has a two technology. And the first is the preview chunking. And the preview chunking is mix the requests on the same GPU and split the long input promotes into smaller chunks and process them across multiple iterations. And this will reduce the long preview blocking and enable the better scheduling flexibility. And the continuous batching schedules the request at the iteration level by dynamically merging the preview chunks and the decode step into the same batch. And it will improve the GPU utilization and reduce the serving latency under the dynamic workloads. But it brings a new question is, how can we divide the total energy in the LLM serving to the single request? And think about it. Imagine the 4 users on this slide, and they request an explanation, some Python code, a wider answer, and the paper summary. And the GPU can tell us its total energy. And the serving system can also report the tokens, the GPU time, or throughput, but none of these numbers directly tell us the energy of one user. And this matter beyond splitting without request level energy information. The serving system also lack of the feedback needed for energy aware routing and scheduling. And about the solution, the overall solution is to divide the energy by tokens. But tokens are not all energetical equivalent. The long promotes and the long answers stress the GPU differently, and the requests running together can share the hardware work. And our experiments make this visible. The prefill energy grows almost linearly, and however, for decode heavy requests, the increase in concurrency for 1 to 10 raises total energy by only about 6%. 10 concurrent requests do not cost 10 times as much, and batch increase the cooperative efficiency. And token-based accounting ignore this shared discount. The leave one out accounting also fail because removing one request can change execution state for everyone else. So request energy is therefore not simple hidden, it's physically entangled. Without knowing a request increment energy, we cannot decide whether to route it elsewhere or delay it briefly for a more efficient batch, or schedule it with different requests. And to address this problem, we need a matrix that reflects the actual serving state. So instead of counting output tokens, we asked whether we could describe the resources that actually dominate decode. Every decoding request maintain a growing KV cache until it finishes. And energy therefore depends on both cache size and the lifetime. And this led us to the KV volume, the area under the KV cache growth curve. In a ride-sharing analogy, and imagine that each passenger has a luggage, and what matters is not only the number of bags, but how much the trunk space has occupied and how long they remain in the car. And KV volume captures this combination. And the second is the phase-aware energy model. With the matrix, we use the phase-aware energy model. The prefill is estimated mainly from the promote length because its energy is nearly the additive. And decode is estimated from the changing KV occupancy and the energy per unit of KV volume. And the equation is not the key message. The key is that the energy per token change greatly with concurrency, while energy per KV volume is much more stable, and the KV volume follows the physical bottleneck and let us estimate the energy of different request groups. Second, we still need to divide the shared energy, so we use the Shapley value. Imagine different passenger pickup order and ask how much extra cost each passenger add when drawing. And averaging this marginal cost across possible orders give each passenger a fair share while preserving the benefits of sharing. And checking every possible order is too expensive, so we sample a limited number with the Monte Carlo approximation. In short, the KV volume describes the occupied resources and sharply divided the shared cost. Together, they turn an invisible quantity into a request level signal that a controller can use. And now let's show the results. And we first compare our model-based attribution with physically measured ground truth. And as shown here, our Shapley-based results closely follow the ground truth allocation, while token-based and leave one out methods show clear bias because they miss the interaction between concurrent requests. And then we implement this idea as what's on LLM. And it's an accounting layer, not a new scheduler. Its role is to expose the energy information that network and serving policies needed. As shown in the architecture, the request passes through an API gateway and the router before reaching a serving instance such as VLAN. And what's on LLM observes two streams besides this path: the core's total GPU energy from hardware and the fine-grained request and the KB cache status from the serving software. It aligns this stream in short windows. Hardware measurements anchor the accounting to real energy, while software traces device at total amount requests. We do not pretend to measure isolated request energy, and we combine a real total with a model of the shared states. Here also is the result. And the evaluation gives us three takeaways. First, the model closely tracks measurement energy on both platforms. Second, the request level allocation stay within about 5% of the Shapley target. And third, the conventional method can deviate by more than 50% because this means cooperation between the concurrent requests. And finally, I would like to thank my co-author, our collaborators, and the Suscom Lab at the Hong Kong University of Science and Technology, Guangzhou, for their support. And thank you for listening, and I'm happy to take a question.
Any questions?
Thank you, very interesting paper. And I want to ask, I think this is they will be good for useful for price hunting for so I think because one point I don't understand for energy accounting, but the energy of the device is changing itself. For example, according to the temperature, the pressure. So this one thing, there is no static energy consumption. I think to consuming. I think is the first thing. Second thing is that I see that you use the KV cache to calculate the price of to calculate the energy consumption during the code phase. But actually the computation efficiency is very complex. For example, the backside will influence the decoding rates and the implementation of the operator also influence that. So I'm not sure whether this model is precise enough, just account for the very cache load. I'm not sure. Okay.
Okay. So for the first question, can you repeat? I just forgot it.
The energy is not a static value, so
The first one.
yes, the first one. Yes. The energy consumption of
I got it. So for the first question, we do not want to get the very accurate energy. We just wanna to attribute the total energy to fairly attribute the energy to the request. So if you wanna if you wanted to get a accurate energy like the temperature will influence the energy, and maybe we can get the truth and energy number from the NVML, and we use our model to just fairly to attribute the energy to the single request. Our goal is to attribute it fairly.
So what can we use it for? For what?
Maybe for the scheduling. Like we can predict the overhead, whether we have to join this request like immediately or delay it later, and to to like energy aware scheduling. Yeah.
I'm sorry, I have to cut it off right here. The second question, you should